Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by the Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the second lecture on the course Maritime Structures. This is offered by Department of Maritime Engineering at IIT Gandhinagar. Let us see what we had a recap in the last lecture. In the last lecture, we learned different types of offshore structures. We also understood that the geometric design of these structural systems are different by two ways. Let us look at the substructure and the superstructure. Friends, just to recollect, substructure is the one which is in water, superstructure is the one which is above water. We already understood yesterday that the substructure part is different for different types of what? offshore structures, and it essentially depends on the water depth. Whereas the superstructure remains almost similar to all types of offshore structures. There is a reason for this, which we explained in the last lecture. As you go deeper and deeper water depths, the geometric form of the structural system need to be different. So, why they are different and how they are different? We will discuss that details in this lecture. So, the second lecture is now titled as Types of Offshore Structures. Having said this, let us start discussing one by one. To start with, we will take fixed platforms. Friends, the title fixed itself make you understand that the bottom of the structural system is fixed to the seabed. This type of structural system is the most primitive type of offshore platforms. Primitive in sense, these are the foremost, fundamental, basic, first models of offshore platforms. So, designers felt if you want to construct an offshore platform in sea, you must fix the bottom of this platform to the seabed. That was the original idea they conceived in 1900s. Let us see how gradually this idea got translated from fixed to floating types. That is where the innovation came into play. So, the most primitive type is a fixed platform. So, the word fixed emphasizes that the base of the platform is fixed to the seabed. So, once you fix a base of a structural system, it is imperative to understand that they become stiff. So, that is very interesting, friends. Fixed platforms are very stiff structurally, and when they become stiff, they relatively become insensitive to lateral loads. Any stiff system will resist lateral loads very conveniently. That is a basic engineering logic. So, fixed platforms are designed to be rigid and stiff, and they are relatively insensitive to lateral loads. What are the different kinds of lateral loads we expect in offshore platforms or maritime structures? We had a hint yesterday telling you that wave loads, wind loads, seismic loads, ice loads, current, shock and impact loads are a few of them which cause lateral push to maritime structures. So, fixed platforms become insensitive to these loads because they are very stiff. Now, the question comes, how the stiffness is achieved in the design? You can achieve stiffness in design by two ways. One, by having large cross-sectional dimensions of the members. Secondly, from the support condition. So, here the stiffness is achieved by support condition. So, we fix the platform to the seabed. Obviously, if this is the seabed, you do not fix it like this. So, you do the other way. You have a member, maybe a tubular member, then this is the ground level. You drive a pile to fix it. So, this is the pile driven into the seabed. This is the column member which is reflected here. So, the fixity what we refer to is this. It is because of this fixity, any lateral load applied to the system the system becomes insensitive because the system becomes rigid and stiff. I hope you understand this. Okay, getting back to this. Designers were convinced that such structures are very suitable for offshore drilling. So, they started using them for oil and gas exploration because they can sustain any extent of lateral loads. The construction methods were developed mostly to install these structures only on shallow waters. Friends, let us try to highlight the important terms which we understand and recollect later. Let us try to highlight them. The first term I want to highlight is fixed platform, bottom is fixed. They are very stiff. They are relatively insensitive to lateral loads. Construction methods were developed to deploy them only in shallow waters. Yesterday we discussed about what is a shallow water, intermediate, deep and ultra deep waters. So, as a thumb rule, we can say that shallow, intermediate, deep and ultra deep all refers to water depth. As a thumb rule, we gave an indication what should be the value of these in meters in the last lecture. But that is not the way how they are classified. Water depth helps you to classify shallow, intermediate, deep and ultra deep, but not based only on the depth of water, but based on some hydrodynamic characteristics. For example, D by L will help you to classify this, where D is the water depth and L is the wavelength. Let us not worry about this classification at this moment. We will talk about this classification later in the lectures dedicated to wave hydrodynamics in the same course. So, let us now understand that the classification of the water depths does not purely depend on the water depth number alone, it also depends on hydrodynamic characteristics. Having said this, we said that the construction methods were developed by the engineers only for shallow water installations. Suppose if you try to install them in higher water depths, what are the consequences? What will be the issue? The issue is the cost will phenomenally increase. Further, it also has increased complexities in the construction process. So, friends, unlike other land-based structures, the complexities in construction, installation and commissioning play a very important role in maritime structures. That is why in this course, we also talk about something called construction and pre-service analysis. This is very unique to maritime structures. You do not have these complexities in land-based structures in civil engineering. Okay? So, now increased cost and increased complexity does not allow a fixed platform to be deployed in greater water depths. It is not that you cannot do them at greater waters. If you do them, you will be compromising on the cost. Now, the question comes, why the cost will increase as you go deeper? Let us look at this slide again. Let us say I have an offshore platform whose substructure is what I am drawing. We know below water is the substructure and above water is the superstructure. So, I am talking about this part. Now, we already said that they will be all deployed using a pile, and they will be fixed at the bottom. We already said that. Okay. Now look at this structural system. This system is made of braces and members. Let us say these are all main members, these are all braces, which are essentially of steel. To get an idea, the diameter of this member will be approximately 1000 millimeters, and the thickness of this member will be approximately 60 to 70 millimeters. So, they are all hollow tubes of external diameter about 1 meter and thickness about 60 millimeters. So, now imagine if I construct this system at a deeper water depths. Let us say I draw another figure where the superstructure is same, but I want to take it to deeper waters. So, I drive it here and this becomes a water depth now. So, this extent of portion of material cost will be higher. So, as you go deeper and deeper, the substructure cost will be kept on increasing, because you have to found them, you have got to fix them at the seabed. So, therefore, friends, fixed structures are not recommended for greater water depths, because it will increase the cost, and of course, the complexities will also grow in terms of construction, installation and commissioning. This is one demerit we have when I use fixed platforms for deeper waters. Furthermore, friends, let us have one more logic of, take an example, let us say we have two friends. Okay. This fellow is about, let us say, 50 kg. This fellow is about 85 kg or 80 kg. Okay. He eats well and he is always foodie, right. So, he is good and he is heavy. They are friends. They go to a movie and another guy picks up a fight with this fellow. Since these two people are friends, when he picks up a fight with this fellow goes for his rescue. So, let us take this example to understand what is the complexity here. Since because this fellow is heavy and he is, let us say, a bodybuilder, he will always have a tendency to fight. Since this fellow is lean, this fellow cannot fight alone. He will give way, his resistance is very less. Since this fellow is his friend, he will fight for him. It means any system which is rigid in nature and stiff will always tend to attract more forces. Okay. So, this is another demerit we have in fixed systems. When you have a fixed platform, they will attract more forces because of increased stiffness. Then how in engineering perspective this is a loss for us? Any structural member which attracts more forces needs to be designed with larger dimension and larger thickness. So, we lose material cost because we are allowing additional forces to act on the members because they are stiff. 1. 2. The construction process is expensive. We all agree that lifting a 1 meter pipe of 50 mm thick is difficult compared to lifting a 300 mm pipe of 10 mm thick. So, when you use a larger dimension, the construction cost relatively goes high. Furthermore, the downtime for commissioning is a very important factor in offshore engineering and maritime engineering. The time taken for construction is going to increase because the member sizes are heavy. You need to have special cranes, special equipments, special team members to commission such large, massive structures. If you do that, then the commissioning cost increases, and reusability is another concern what we have in maritime engineering today, because as per the international norms of environmental protection policy, it is understood that all structures should be sustainable and environmental friendly. Whereas we all know steel once get corroded, it's waste. We cannot reuse them. So, reusability is a big question when you dump massive amount of steel in water. So, increased water depth, increased stiffness will not help the structures to go deeper waters. So, fixed platforms are meant only for shallow waters by design. Remember that, friends, if you really wanted to use them for deeper waters, there is no stoppage on that. One can use, but that will not be a good idea in engineering perspective. Having said this, let us see photographs of a few of them. I am not showing a real-time photograph of the platforms because that may attract copyright problems. So, these are all redrawn equivalent images of a platform. You can see here, this is a Bullwinkle platform commissioned in USA, a fixed platform. You can also see this is my substructure, and you can see the legs. Okay, these are nothing but column members, and these are the braces. Look at the top side. Now you will be able to recollect the name of few of them. Can you name this what it is? Yes, this is what we call as a flare boom, because there is a flare here. This is also called as torch in offshore engineering. This is the drilling derrick which helps me to drill oil into the seabed. Can you name what this is? This is nothing but a crane, and here it has got a hook which we are going to design this in this course. And these are all truss based systems. These are all living quarters, electromechanical systems, and I think you will be able to recollect this easily. There is a H written here. So, this is nothing but a helipad. So, the top structure is mostly congested with steel components and electromechanical systems. A typical platform of fixed type looks like this. A Bullwinkle platform is a classical example of a fixed platform. Amongst the fixed type, many of them were constructed in US. For example, Bullwinkle, Pompano and Harmony. You may be wondering how these names have been given. These names are not a name of a scientist or name of a person who construct these platforms. These are actually given based upon astrological naming. I mean, we may not believe this, there is no proof for this, but they do not give these names just like that. Sometimes they are also named after the location or the city where they are. For example, Harmony was executed after an MOU was signed between US and other country for exploring oil. So, Harmony is related to that kind of name. The bracketed values will tell you at what water depths they are commissioned. For example, Bullwinkle is the deepest platform fixed type commissioned in USA, is about 412 meters. So, let us look at what is the commercial value of this kind of platform, because we would like to know if you go for any type of engineering construction, be it a building mall, be it a library, be it a studio, be it a theatre, be it a school, we always look for what we call return on investment, the commercial model. Let us look at the commercial model of a maritime structure like an offshore platform. Each platform can produce approximately 35,000 to 60,000 barrels per day, BPD, barrels per day. Now, one may like to convert this barrel to liters. Approximately one barrel is about 160 liters, okay, 160 liters. Let us take a calculation, let us do a simple calculation. Let us take 40,000 capacity into 160 liters. This is one day, friends. Let us say the platform is operating all 365 days, because I do not think anybody will close down the platform once the platform starts producing oil. And you know, as per Indian rupee, 1 liter of gasoline is costing you approximately 100 rupees. Okay? Look at the revenue in 1 year. You have to only count the zeros. Okay? You have to count the, it's approximately 100 crores from one platform in a year. USA has got about 36 such platforms for the past 75 years. Imagine the money, imagine the revenue. So, we are looking at a very big production value, but it is very interesting for you to also understand that all these platforms will not give you the same capacity of oil production throughout 75 years. That is agreed. It keeps on depleting. As you keep on sucking oil from the seabed, oil formulation will get reduced. So, one platform in 1 year can generate so much revenue, friends. It is a very interesting conceptual idea. Therefore, every country, every organization, every company, every individual wants to own a platform. This is one of the lucrative business in the world. So, maritime engineering is not only an engineering on science or science on papers and pen. It is a practical implication of livelihood of society, because we live and we earn through this living. So, we now realize that a fixed platform, for example, produces so much revenue. Approximately, I am giving an approximate, I have taken only 40,000. There are platforms which has got 70,000 or 60 million barrels per day. Big platforms are also there. I am just taken only a very basic value of this number. Okay. Having said this, let us look at one more platform which is called Hibernia. I want you to pay attention to the geometry of this platform, friends. You can look at the bottom, they are different from this. Okay. These are caissons, whereas this is a steel truss. So, the substructure is significantly different from the previous platform. Both are fixed at the bottom. So, fixed platforms can also have different substructure. So, why this platform is different? Because this platform is constructed in concrete, whereas this platform was constructed in steel. So, material use also vary the design configurations. Hibernia platform is commissioned in Canada at just 80-meter depth, just 80 meters. That is the depth of water. The platform was constructed recently, 1997. Canada is a country which started exploring oil very recently, about 30 years back. I mean, not, in fact, India did much ahead of Canada. One of the important design feature of this platform is this is a gravity based structure. We call this as GBS. So, one can get a notion of what is gravity based. Once I have a colossal weight of this caisson, very heavy, the platform rests on the seabed by its self weight. There is no need for piling. If you recollect what we did earlier, they had piling, whereas this platform there is no piling. So, the construction cost is different from the previous platform. So, there is no piling, but this rests on the seabed on its own weight. But then if you ask me a question, does it have any demerit or merit? Let us talk about that. GBS platforms do not require piling. They resist lateral load by the self weight. So, the catchword here is self weight. Friends, I would always love that you keep on marking the important keywords in every slide as you keep on watching them, because we will try to recollect questions, tutorials based on this later. You need not have to go through the entire lecture again. Look at only your keywords, you will be able to answer me tutorials easily. So, GBS platforms resist by self weight, but to improve the lateral resistance, they need additional feature called skirt piles. The skirt piles need not be for the entire depth of seabed. So, then the question comes, what is a skirt pile? We will discuss about this design later in geotechnical aspect of this course in different lectures. So, skirt piles are different from conventional piles as you see here. Okay, they are different. So, skirt piles are required to improve lateral resistance. So, look at the superstructure. I think you will be able to recollect what I am answering again. A flare boom, a drilling derrick, a helipad, living quarters, cranes, electromechanical systems. Okay. So, top side looks almost similar, whereas substructure is different. The third type of a fixed platform is called a jacket platform. You know, jacket is always a cover what people used to put on their body. If you feel cold, you put a jacket, you wear a jacket. When you drive a motorcycle, you wear a jacket. So, jacket is a cover. Okay. So, similarly, jacket platforms looks like truss based system, which is a complete assembly of truss members. Essentially, jacket platforms are constructed by steel. So, steel jacket platform is a fixed type platform. It consists of a tower. You can see there is a tower here. This tower is prefabricated and then it is towed. See this figure. A big tower is being towed by a small vessel. Why? Because this can be kept on a tugboat. This is what we call the tugboat. This is a vessel which is dragging this, and it is made to sail until it reaches the site. We talk about these details in commissioning later. So, steel jacket platforms essentially consist of a truss type tower, and why they have been made a truss type? It is very interesting, friends. Let us look at this understanding. If I have a wall, let us say I have a road banner. Let me talk about this. Let me take away this. Let us say we all drive on highway. On the highway, you will notice there are a lot of roadside banners. You will notice them. Okay. No, you must be noticing that there are a lot of personalities whose figures are appearing on the banners. We will not talk about that. Let us say there are something written, the banners. If you closely look at these banners will have lot of micro pores. So, the wind is allowed to pass through them. Suppose we do not have this micro pores, you make a solid banner. Okay. Wind is not allowed to pass through. The banner will tear off, will break. So, any structure which is transparent to lateral will always resist the load better. So, transparency resists or help to resist load. Similarly, when this system is transparent to wave loads, wave passes through them and that helps to alleviate these loads much in a comfortable manner. So, steel jackets are prefabricated in offshore site and then transported to the site using barges. What you see here is a typical barge. Once they reach the site, they are appended. We will talk about this much later in the construction steps and analysis. They are appended and they are placed in position. So friends, once the jacket is constructed, it is lifted and appended. You can see this is slide number 1, it is lifted. This is slide number 2, it is appended. You can clearly see how the jacket is being lifted using a tool here. Okay. So, these are all very interesting construction methods of maritime structures which will help you to understand in detail in the coming lectures. So, then once this is laid and constructed, the whole module is fixed over this. This is called building module. Then the whole platform is ready. So, this is the platform what we saw earlier also. So, flare boom, drilling derrick, crane, helipad, living quarters, electromechanical systems and the jacket. So, this is prefabricated and the schematic diagram looks like this. Okay. These are about fixed platforms. If you have any specific questions, please put them to me in my email. So, we already said that gravity platforms, which are called as gravity based structures, have a very high self weight, what we call as colossal weight. See, when you start learning maritime engineering, the vocabulary is also very important. The technical terminology is to be learnt in the same manner. So, colossal weight refers to self weight of the platform is very high. These platforms do not require piles, but they are resting by its own weight. Therefore, they are called gravity platforms. They are suitable up to water depth about 350 meters. These caissons are hollow in nature. I will show you a caisson. They are hollow in nature. These are hollow. These are hollow. So, this hollow space is used to store oil. See, this hollow space, which we call as a void space, is used to store oil. Some of the good gravity based platforms are Troll 300, Dragon, Troll platform, Brent platform, Ninian platform, Maureen platform. Most of them are constructed in US, Canada and UK. None of them are in India. Okay. So, these are some of the names of the gravity based platforms which are commissioned in different waters. The third type of platform, what we see here is jack-up rigs. The name suggests jack-up, and the rig is a conventional rig being used for exploring water from surface soil. So, drilling rigs are generally used for exploring water from earth's surface. Similar concept is used here for exploring oil and gas from seabeds. Why they are called jack-up? I will explain this. The drilling rigs essentially consist of legs to support them. Let us see a typical jack-up rig. It is a typical jack-up rig. This looks like a vessel, a ship which is sailing. When the ship sails, all these legs will be raised up. Okay? All these legs will be raised up. For example, the ship looks like this. This is how the legs are raised up and the ship sails. When the ship reaches the site, it has been commissioned here, the ship comes here and by a mechanism of pushing this up, this is raised and the legs go down. That is why this is called jack rigs. You know, jacking, you have a four-wheeler, you want to change your tire when it's deflated, you use jacks to raise the laden weight of the vehicle and change the tires. So, jack is a concept where people generally use for hydro lifting. Similarly, here the deck is hydro lifted and the legs are inserted down. Okay, once it is down, it looks like this. It looks like this. Okay, they are called jack-up rigs. So, jack-up rigs actually are supported by legs and the hull is being used for exploration. So, in this is what we call as a hull. We will take about 5 more minutes to finish up this part of the lecture. So, pay attention and you do not miss any important point on the jack-up rigs. So, they are essentially supported by steel lattice towers. The top side is more or similar to any GBS or a jacket platform, where the substructure is now different. Earlier, in GBS and in jacket platforms, the substructure was not movable, they were fixed, whereas here the substructure can go up and down like a jack-up rig. Okay? So, now you can see, as you keep on increasing the depth of operation from a fixed type to intermediate waters, the substructural design concept is changed. Okay? It is a similar cargo vessel which is being modified to go for a jack-up rig. The name jack-up is already explained how the legs will be pulled up when the jack-up rigs reaches the site. So, the geometric design of the superstructure is comparable with the fixed platform, but the substructure design is different. So, the foundation of jack-up rig is a very important aspect with which we close this lecture. The foundation is being used something called a spud can system. Please pay attention to this figure. It's an inverted cone. People play actually with this kind of design in your hobby days. So, if you have a tumbler, if you have a glass, let us say, if you have a glass, you have a plate, you clean the glass and put the plate, the glass empty, inverted, and you will see because of vacuum, the glass or the cup will be fixed to the glass. Okay? You can lift the glass with a cup, it will not fall. There is a vacuum pressure acting here. The same concept is applied here. So, you do a spud can, it's an inverted cone, you press this spud can into the clay soil, vacuum is created and that becomes a foundation system for a jack-up rig. This is what we call as a spud can foundation system, which will now help to resist the lateral loads like wind and wave on the jack-up rigs. Spud cans are suitable only for stiff clay and sand. Therefore, these kind of structures cannot be commissioned in rocky bed. Okay? They can be only suitable for stiff clay and sandy waters. Once the spud can is fixed firmly, it accumulates soil particles in the void space and helps to resist the lateral load acting on the jack-up rigs. Remember friends, it requires a very heavy pull-out force to remove the spud can. It cannot come out automatically. Okay? You have to loosen the soil by pouring water or by sucking the granular material, then only can remove this foundation. It is a very rigid foundation in that sense, but there is no piling. Remember that in jacket structures we had piling, in gravity based structures we have caissons and skirt piles, whereas in jack-up rigs we have spud cans. So, the foundation system, the substructure system are different for different types of fixed structures. Okay friends, we make a summary of this lecture, what we have learnt. The summary says we learnt about fixed platforms. In this we learnt about steel jacket structures. We also learnt about gravity based structures. We also learnt about jack-up rigs. We agreed that the substructure is different, the superstructure is more or less same, and the foundation type or different. If you have any specific questions, please email us in SwayamPrabha. We will try to help you whatever doubts you have. Thank you very much. Namaste.